Hello, my name is Grayson Cupit. I'm a research engineer with the Institute for Intelligent Systems at the University of Memphis in Tennessee, where we do work with AI and machine learning as it pertains to education, linguistics, political science, robotics, all sorts of other fun stuff. I'm currently there as a member of the Languages Across Cultures Lab, where we're working on a Minerva Initiative grant sponsored by the Department of Defense, and that grant supports this research as well. What is it about a piece of propaganda that allows some readers to pick up on its credibility immediately just by reading the text itself? There has to be some sort of linguistic cue embedded in the language that allows those readers to do that. And if those cues are there, can we teach them to a machine? That's sort of the intuition behind this project and behind today's talk. But first, a little bit of background. So in the age of social media, propaganda often goes by another name. That's fake news. So these are stories typically masquerading as credible content on sites like Facebook or Twitter. And they can range anywhere from heavily biased to deliberate disinformation. Our research corroborates what other people have found, and that the most successful of these fake news stories can be engaged with at a much higher rate than the most successful credible news stories out there. And that's a growing problem not only for individuals who want to discern what is fact and what is fiction, but it's also an issue for people who would help those individuals by classifying it, labeling it as such. Most of the sort of classification schemas to date involve either human curation, and some of the best performing ones that we've seen rely on mining graph data from social media networks. So that's not really ideal. What we propose is a completely automated classification schema that relies only on linguistic features of the text itself. And in this way, classification can happen more or less in a vacuum, devoid of any context other than the text. And in the process of doing that, we seek to answer the question, what linguistic cues do fake news stories rely on to engage and promote interaction? And how can we use those cues to automatically differentiate fake news from real news? So before I talk about the classification schema, I have to talk a little bit about our data set itself. So for our fake news data set, we use the Kaggle Getting Real About Fake News data set. This consists of about 13,000 stories. When we take that, we discard non-English stories, stories that have no title or no text body. We get a corpus of 11,568 articles and 11,568 headlines. We supplement this data set with a real news data set that we assemble ourselves. We use the BuzzSumo service. This is a web service that returns headlines, URLs, and share counts for articles, news stories that appear on social media sites. When we query BuzzSumo for articles coming from sources that are widely considered to be reputable, such as CNN, Reuters, Fox News, we get 10,998 such data points. And when we construct a suite of HTML web scrapers in Python, we're able to retrieve the full text articles of 6,081 of those stories. We collect these four corpora, and we want to talk about how we can mine linguistic data from them now. So there are a lot of tools that we can use to do this, but we first choose LIWC, which stands for the Linguistic Inquiry and Word Count tool. LIWC is at its core a dictionary-based bag of words model. It's been widely used in every domain under the sun, and what LIWC is capable of doing is taking a text and returning to you 80 different variables that measure not only the grammatical processes, so pronoun and punctuation usage, but also psychological ones. So cognitive processes, affective processes, perceptual processes are all measured by LIWC. So for each of our four corpora, real and fake, headlines, and articles, we process the text using LIWC, and we store those results. Before we classify them, we want to get an idea if there are significant differences between these linguistic features between fake and real news stories. So we see here the results of a two-tailed independent samples t-test comparing the article language of fake news to real news. This is just a sample. There were actually many more variables that were significant at the p less than 0.05 level, but with this many data points, it's really more important to pay attention to the effect size, which is presented here as Cohen's d. So these were calculated using subtracting the real mean from the fake mean. So when we see this negative sign here in the here variable, for instance, it means that fake news uses, on average, much less hearing language than real news articles. And so we chalk this one up to journalistic style. Traditionally, journalists might be hearing reports from the White House, for example. Fake news stories are much less likely to protect their journalistic credibility by padding their language with that kind of thing. This falls in line, too, with the certainty variable. We see that fake news uses a lot more certainty language on average than real news. We also see that fake news is much more focused on the present, and fake news is also much less focused on the past. It's also more exclamatory, and that's a grammatical process variable that actually measures your punctuation usage. So a lot of these effect sizes, we see some large to medium effect sizes from a lot of these variables. So we've established that there are some significant differences between the language of the two categories. And now that we've done that, we'd like to get an idea for how they cluster in a linguistic space. So we see here the results of a t-stochastic neighbor embedding, which is, or t-SNE for short. And that's a way to take high-dimensional data and embed it in a low-dimensional space, in this case 2 dimensions, while preserving the local structure of that data. Before we do that, we use a truncated singular value decomposition to compress it down to 70 different variables, and we visualize the results. Here on the left, we see the t-SNE results of the headlines. And so you see there are definitely some outliers here where the headline information is enough to categorize the data point correctly. Most of it, however, lies in this sort of unseparable mass in the middle. So we can kind of interpret that as saying that the headline language is usually not enough to make a correct classification, but sometimes it is. On the right here, when we look at the text of the entire article itself, the story changes. We see 2 distinct locales arise, and that gives us a lot of confidence that there's some good information in there in these linguistic variables. So we use these features, not the t-SNE, or excuse me, the SVD, but the raw Luke variables as the input space to our model. We use what would be considered a deep neural network. That is, we have 2 hidden layers between input and output. They're comprised of 50 and 20 perceptrons each, respectively. Each perceptron is using the rectified linear unit activation function. Because this is a binary classification task, we use the binary cross-entropy function as our loss function to minimize. Likewise, because it's a binary classification task, we can interpret this output layer using the sigmoid function directly as a certainty score or a probability. Finally, we fight overfitting by penalizing our weight updates during backpropagation with the L2 regularization term. And so we train this model twice, once on headlines and once on the articles. Our performance on the headlines, we see for each training set, we split it up into training, test, and validation sets. We see here in purple, we see the validation loss, and in orange is the training loss. Black up here is our training accuracy, and the teal is our validation accuracy. So for the headlines, we see that both loss functions converge to minima fairly quickly. As the training loss decreases, we see an increase in our training accuracy. However, our validation accuracy remains more or less the same. So without regularization, we likely would have overfit this model. As it stands, it's just a little bit less than impressive. As you can see, we never get higher than about 73% accuracy or so on samples that we've never seen before. When we look at a receiver operating characteristic curve, this is likewise pretty unimpressive. Our ROC, our area under the ROC curve is equal to 0.08. But again, just like the t-SNE visualizations, when we look at the full text of the articles, the story changes a little bit. So here, we see the same graph. Again, loss functions converging to minima. This time, however, we see both the training and validation accuracy increasing together as the loss functions decrease, giving us an idea of that this model generalizes pretty well. Again, the validation accuracy in violet is much better this time as well. We actually approach 87% accuracy or so on samples that we've never seen before. When we look at the ROC curve here, we see that this model is capable of true positive rates approaching 90%. while keeping false positive rates below 20%. The area under this curve is 0.93, indicating a pretty good performance overall. So what can we take from this? Well, the first conclusion is that headlines don't tell the whole story. But more interestingly, we've shown that there are purely linguistic channels that actually carry a lot of information that we can use to differentiate propaganda or fake news from real credible news stories. In the future, we've got some different directions that we'd like to take this. The first is enriching the model using different sets of linguistic features such as LDA topic modeling, cohesion metrics. But we'd also like to understand better which of these linguistic features make for a successful news story. To that end, we've run a battery of F-tests, testing how well each linguistic feature serves as a regressor for the total share count across all social networks as measured by BuzzSumo. And we see that, again, there are some differences. Now, these are for headlines. If we look at fake, we see some F-scores are really high for the tentative language variable as well as the differentiation variable. And then it falls off pretty sharply here for the rest of these. When we look at real news headlines, we see a much tighter spread. The best predictor ends up being word count or words per sentence, but everything else is more tightly clustered around a norm. There are no real standouts. So this is some pretty interesting work that we're going to pursue in the future. So with that being said, I'd like to thank you for watching. And if you're so inclined, please check out our blog if you'd like to know more. The URL's there on the screen. Thanks so much.